Yeah, it's about time to start. So go ahead and chat me your first and last name before we get started. You can go ahead and do that now. Hey, Chloe, I just advised them to go ahead and chat me your first and last name. So go ahead and do that if you haven't already. And everyone else, we're getting ready to get started. Anybody have any questions before we do get started? So next week is our technically our exam week. No one said they had any questions. I didn't hear anybody anyways. Feel free to start typing in chat if you have any. But next week is sort of our exam week. The way I moved everything, you have a online test that's due tomorrow by 11:59 p.m. I may or may not give you another online test. Don't worry about it if it turns out to be something that you end up missing. This probably means I'm just going to drop my two lowest online tests instead of one lowest. So if I end up getting people missing that last test, it's not going to harm your grade necessarily. So I'm going to go ahead and probably do that. The only reason I'm doing it is a lot of students get a little bit of comfort from taking an online test that exactly matches the material that they're going to get on the face-to-face test, or in this case, the final exam. So if I make it, it's for that reason. Uh, and I'll probably, like I said, bump the number of dropped online tests to two instead of one. We have our face-to-face tests Monday. Well, you guys can take it as early as tomorrow, but you can take it as early as tomorrow and you can take it as late as a week from tomorrow for the online classes. But if you need a proctor, you're welcome to come take it with me at any of those times I said yesterday. I think it was 8:30, 9, 9:30, 10, 10:30, all the way up to 2 p.m. if I remember correctly. So you can do all that on Monday. Any of those time slots you want to come in. If you have a computer, bring it. If you don't, that's okay. We have one for you. So that's completely open. And then the exam is supposed to be Wednesday. That'd be a week from today. I've already made the practice final. It might not be. I think I already put it up in this class. If not, I'm going to check right after class to make sure. So the practice final either is already up or it will be up, and it does include chapters 14 and 15. Uh, that you have to do sometime next week, but the very latest you can do it is you have to have it completed, not started. You have to have it completed by 2 p.m. on Monday. But again, that requires a proctor as well. The testing center has been alerted that you guys will be coming for that, so you certainly have that on all the campuses. And if you still can't find a time to fit your schedule, contact me. I may or may not be able to help you. Okay. So, anybody have any questions before I get started then? All right. Well, we had a couple examples that I wanted to finish up in chapters 10 and 11. And the chapter 14 stuff that I plan on covering is I'm going to do that in a series of videos that'll come out. I might make some tonight, but I definitely will make tomorrow and Saturday and maybe even Sunday. But anything I don't have done by Sunday, then it's just not going to be done. Not only that, if you guys pay close attention, like I'm going to monitor my dashboard for my YouTube channel. And if you guys are actually watching these videos I've been sent you, I'm less inclined to feel required to test you on that material because at least you're covering it, especially if you go ahead and do the homeworks for chapters 14 and 15 as well. So if you do the homeworks for chapters 14 and 15 and you watch the videos, there is a really good probability that I might not even include test questions on the final exam from 14 and 15, just because of the way I'm covering it. Not because it's not important, because it really is. But there's very specific details about 14 and 15 that are important. I hope to mention them a little today, but mainly I got to knock out chapters 10 and 11, and then the rest will be done through video. So, anybody have any questions now that I said all that stuff? All right. Well, just keep an eye on my YouTube channel and that sort of stuff. Let me know if there's anything I can do to help you. Again, I have all those testing times. I might even find some more other than the ones I mentioned. So if you can't use those for your proctoring time, then let me know. Maybe I can find something else, or you can just set it up at the testing center. So I'm going to go ahead and share my iPad screen with you guys. Okay, so we've got that now. Uh, what I wanted to talk about is we already know kinetic energy is 1/2 mv squared. And you probably can use the rotational analogs of mass and velocity to figure out what the kinetic energy of rotation is. In fact, that's exactly right. In place of m, you put I, and in place of v, you put omega. So the kinetic energy in rotational motion is 1/2 I omega squared. But it's not instead of, it's in addition to. So if you're thinking, for instance, this Rubik's Cube flying through the air, if the Rubik's Cube is a point particle, then the fact it's spinning or not doesn't matter at all because none of the energy goes into a point particle because it physically has no dimension. But when it's not a point particle, it could fly like this where it doesn't rotate, but it could also fly like this where it's doing that. So it's got energy associated with it, kinetic energy like 1/2 mv squared that's related to the center of mass moving at velocity v. But in addition to that, rotating about a particular axis, we have a kinetic energy 1/2 I omega squared. Now, as a projectile, that's not too big of a deal because those two velocities, the angular velocity omega and the linear velocity v, aren't related. But if you're talking about a rolling object, specifically a rolling object without slipping, then there's a definite linkage between the velocity at which something rotates and the velocity at which something translates. So if you're thinking in terms of this round object rolling like this, when it rolls one whole circumference, that means the distance traveled is one whole circumference, and that means the angle traveled is 2 pi radians, and the amount of time taken would be however long it takes, but the velocity, the linear velocity, would be the circumference divided by the time taken, whereas the angular velocity would be the angle 2 pi divided by the time taken. If you look at it that way, you'll realize there's definitely a linkage. Specifically, v is equal to r times omega, where omega is the angular speed. That also allows us to say a, the linear acceleration, is equal to r times alpha, the angular acceleration. So when things are rolling, especially rolling without slipping, you have that linkage. And that gives you yet a third equation to analyze when you're, for instance, talking about masses on pulleys and so on and so forth. So just remember the 1/2 I omega squared does not replace the 1/2 mv squared. It's almost always in addition to. Now that we have that, what we're going to do is do some specific examples. So, for instance, I'm going to talk about a flywheel, and I'm looking at example, just like the example in the book, example 1015. It says flywheels are simply large rotating discs. They have been suggested as means of storing energy for solar powered generating systems. Estimate the kinetic energy that can be stored in an 80,000 kilogram flywheel with a diameter. Excuse me, with a diameter of 10 meters, about the size of a three-story. What the heck? Diameter of 10 meters. They said that's a three-story building. Yeah, that's about right. Assume it could hold together without flying apart due to the internal stresses. And we're talking about this disk rotating at 100 miles per hour. So what I have here is some information. We're going to call this example one. What I have is a rotating disk, and the rotation rate is omega equals 100 revolutions per minute. The mass is 80 times 10 to the third kilograms, and the radius is equal to the diameter over 2, and they gave us the diameter was 10 meters, so I'm going to call this 10 meters divided by 2. And I'm assuming all these things have at least 2 sig figs, so this one's going to be 5.0 meters. And what we want to know is how much energy is stored. So E, which in this case equals K, is question mark. That's really what we want to know. So in this case, we don't have a disc rolling across the road or something. So we don't have a 1/2 mv squared term. All we have is a K equals 1 half I omega squared term. Okay, that's the actual energy that they're asking us to estimate, and it only has that because the center of mass is not moving, so the velocity of the center of mass is zero, so the 1 half mv squared is zero. Okay, so what I'm going to do is I'm going to take this 100 revolutions per minute, and I'm going to convert it to radians per second. For instance, I know that one revolution is equal to 2 pi radians. And I also know that 1 minute is equal to 60 seconds. So what I'm going to do is take 100 and multiply it by 2 pi. And I just type in pi, 3.14159. That's more than enough digits. And now that I've multiplied 100 times 2 times pi, I'm now going to divide that answer by 60. And I had 628.318. Now dividing it by 60, I get 10.47. And I'll call that 47 with two extra sig figs, and that is radians per second. Now that I have that, I can estimate the kinetic energy as 1 half I. And for a circular disc, this happens to be one of the videos I made for you guys. Whether the disc is thick or not, it's 1 half mr squared. So I'm going to put in 1 half m r squared, and then I'll close that, and then it's times omega squared. So now I have 1/4 times the mass, which is 80 times 10 to the third kilograms, times r squared, which would be 5.0 meters squared, times omega squared, which is 10.47 radians per second, and that's squared as well. So now when I do all this math, I'm going to say 0.25, because that's what 1/4 is, times 80 times 10 to the third times 5 squared times 10.47 squared. And that gives me 5.481, carrying two extra digits again like I had before. That's 5.481 times 10 to the seventh. And the unit should be kilograms meters squared per second squared, which is a Newton times a meter, which is a joule. So this is on the order of 10 million joules. Now, the way that would work is you just have this big, giant, let's say, concrete or stone disc or something like that, and it's probably boxed off. So if someone bumps into it, they're not going to, slow it down or anything. So they probably got a circular box that would be built over it, but the axle of the disc is actually probably you'd have some nice sealed bearings that are normally lubricated, regularly greased, and that sort of thing. There will be a shaft sticking out of it, and there's probably some kind of clutch mechanism where you could walk up to it, you'd push the clutch down, and that would basically flip a little lever that allows the axle to sit to continue spinning while the part that allows you to connect to the axle would just sit still. So the axle would be rotating like this, but by popping that clutch, this other part that you could insert some device to or connect some device to, that's going to stay still so that you can connect it. Then you let off the clutch, and it'll slowly speed the wheel or the axle up with the little part that was previously not necessarily connected to it. It's connected to it, but the clutch separate the rotation rates. When you let off that clutch, it's going to slowly speed up to the same speed as the axle, and then you could use that like if you wanted to run a fan, you wouldn't necessarily. I mean, you could in principle run it through a generator and make that run a fan, but you could also just stick a fan axle in the end, and the fan blade would spin like that. So that's one way of tapping the energy. Another way is you could connect it to an impeller, and that impeller could actually sling water and produce a low pressure differential. That pressure differential would actually cause water to be pumped. So that's how you could pump water, that kind of thing. So that's the way you would use such a device. But it's one of the mechanisms that we've considered when it comes to how do we store energy in outer space. And one of the ideas is a big giant disk that rotates. So, anyways, that's an example of how to calculate that, and that gives you an example of how 1/2 I omega squared works. Your book got 5.5 times 10 to the seventh. I got 5.48 times 10 to the seventh. So that's all good. Uh, Now we're going to do some more problems, and this time we're talking about rolling without slipping and stuff of that sort. So I'm going to work this example. What will be the speed of the center of mass of a uniform solid sphere of mass m and radius r0 when it reaches the bottom of an incline if it starts from rest at a vertical height h and rolls without slipping? So that's a very typical problem. I'm going to go ahead and draw it up in such a way that you know what I'm saying. This is very much like example 1017. What we're doing here is we're going to have an inclined plane like this. That inclined plane makes an angle theta, but in addition to the angle theta, we can think of the height right here as being h, okay? And we can think right here of a ball. This is an actual sphere. The sphere has a mass, big M, and has a radius r0, and it's a solid sphere. What we'd like to know is if it rolls without slipping, what will be the speed of the center of mass at the bottom? So when this falls down, dot, 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 it's going to roll off this way, and it's going to be moving with a velocity v, and we want to know what that velocity is. So that's the problem in a nutshell. I can say solution. Everybody understand the problem, by the way? Feel free to ask me a question if you don't. I'm going to put the chat up in case y'all type something. All right. So, uh, what I'm going to use is conservation of energy. And remember, our conservation of energy was U initial plus K initial plus work in equals U final plus K final plus E loss plus work out. Well, we're not dealing with any of those special things here. So the work out is going to be 0. The E loss is going to be 0. The work in is going to be 0. We could, in principle, set the height so that the final potential energy is 0. But I think I'm not going to do that just so you'll have some sort of physical feel for it. What I'm going to do is imagine that the ground height right here is y equals 0, and our potential energy, U, is equal to m times g times y for an object of mass m. The kinetic energy, of course, is 1/2 mv squared, and that's due to the center of mass. And then we also have kinetic energy of rotation, which is 1/2 I omega squared. Now, the sphere also has a moment of inertia given by 2/5 m R0 squared. That's something because I've derived, I know it off the top of my head, but it's also in the table of moments of inertia, which you'll see has been in your tests for the whole semester. Okay. So now what I'm going to do is now that I've gotten zeros for all those quantities. Oh, and I should say the initial kinetic energy is going to be 0. Oops, I should have marked that in red. So the initial kinetic energy is 0. So now I have that version of potential energy or of conservation of energy left, which says U initial is equal to U final plus K final. So now I'm going to fill all that in. The potential energy initial is going to be the mass of the sphere, m. Oops, I'm supposed to be writing in blue. It's going to be the mass of the sphere, big M, times gravitational acceleration, h, or excuse me, g, times the height, which will be the height of the center of mass of the ball. So the center of mass of the ball is one radius higher than the bottom of the ball. So I'm going to say the height is h plus r0. And you'll see that that's not going to cause any problems. Now everything else on the left hand side is zero, but the stuff on the right hand side, when the ball gets to the very bottom, notice its height is still going to be r0. So I'm going to get mg r0 for the final potential energy. And I'm also going to get 1 half mv, which is technically the center of mass velocity. So sometimes you might even write cm next to the v as a subscript. I'm not doing that though. Ooh, and I should make that m a capital M because that's the only mass we're dealing with. So there's your capital M. That's the kinetic energy associated with the object rolling at a velocity v. Plus, I have the kinetic energy associated with the object rotating about its center of mass with an angular velocity omega. Okay. So you can see right now that, well, you probably can't yet, but when I put in I equals 2/5 mr squared, I think you're going to see that we're going to have an I everywhere. And in fact, the left-hand side is going to become mg capital H plus mg r0 is equal to mg r0, which immediately you can see that I can subtract out mg r0 from both sides. But to continue on, I also have plus 1 half, oops, went to red by mistake. We also have plus 1 half mv squared plus 1 half. Now I'm multiplying that times 2/5 mr0 squared. And then omega, I'm just writing that as squared. But rolling without slipping, that tells us that x, the distance traveled linearly, is equal to r times the angle theta that you rotate through. In this case, it'd be r0. And taking the derivative of that, that tells you v is equal to r0 times omega. And if you took the derivative of that, you get a is equal to r0 times alpha. So this is the ramification of rolling without slipping, and I'm specifically going to use that one. They asked us for V, not for omega, so I'm going to eliminate the omega in terms of V. Now you can see also that we have a mass in every term, so what I'm going to do is divide the whole equation through by mass, and that completely disappears. Now I can say that I have G times H is equal to 1 half times 2/5 is equal to 1/5 R0 squared. And then omega is going to become V over R0. And that quantity is squared. So you can see that the R0 up here is going to cancel out with the R0 down here. And oops, I left off a term. We're also going to have the plus 1 half v squared. I just skipped it when I was writing. Everybody sees how I got this now? No one has any problems with it? All right, so now what I have is GH is equal to 1/5 v squared plus 1 half v squared. The least common denominator between 5 and 2 is 10. So I'm going to multiply the 1/5 by 2 over 2. So that's going to be 2/10 v squared. And I'm going to multiply the 1 half by 5 over 5. So that's going to be plus 5/10 v squared. So I get g times h is equal to 7/10 v squared, which means v is equal to the square root of 10 over 7 times g times h. That's the velocity at the bottom. Any questions on that? Now notice if we just drop that ball a height h, we would have gotten the square root of 2gh. That came from kinematics. V squared equals v zero squared plus 2 times g times x minus x zero. That was one of our kinematic equations. If you solved for v final using v zero equals 0, you'd get the square root of 2g times the distance traveled, which would be h or y or x or whatever. So in this case, we got 10/7, which is a little bit smaller than 2. So this thing does roll down the incline, and if it were actually sliding without friction, its velocity at the bottom would have been the square root of 2gh. But because it rolled, some of the energy was stolen to make it to take away from its kinetic energy of translation, because it now has to have a sort of, in some sense, an equal amount or an appreciable amount of kinetic energy associated with rotation. So some of that energy took away its ability to speed to get a higher speed. Any questions on that one? So that's how, excuse me, that's how the conservation of energy can be used when you're dealing with rotational items. Now, another problem your book does, and it's really a conceptual example, it says several objects roll without slipping down an incline. So this is, again, you've got that linkage v equals r omega that ties the linear velocity of the center of mass to the angular velocity of rotation omega through v equals r omega. But it says several objects roll without slipping down an incline of vertical height h, all starting from rest at the same moment. The objects are a thin hoop. So we're going to talk about a thin hoop. We're going to talk about like a wedding band, in other words, a spherical marble. So this is a solid sphere. Oops. A solid sphere. And we also have a solid cylinder. And we also have an empty soup can. And let's see. That's it. Now, what we are told is the initial height is h, and it is an incline, and all objects have the same mass, so they all have the same mass, and they all have the same radius r. So what we're picturing here is an inclined plane. The angle, it has an angle, but we're not given it. It doesn't really matter. The main thing we're doing is sort of like we did last time, which suggests that this height is h. And what we're asked here is, in what order do they reach the bottom of the incline? Okay. In what order? So, really, what matters is if you look at when they reach the final point, the very bottom, they're going to have some speed. And that's going to be how fast they're going at the very bottom. But in some sense, the fastest one will have went faster all the way down, and the slowest one will have went slower all the way down. So if we can just figure out what's the fastest at the bottom, then we can go on the assumption that the one that was fastest at the bottom was the one that made it to the bottom first. Okay, just because we expect it to be a little bit faster in each case. So if we talk about it in terms of conservation of energy, I can go ahead and use this, the same equation we had a second ago, only I'm going to do something kind of neat to deal with the moments of inertia. So I have U initial plus kinetic energy initial plus work in is equal to U final plus kinetic energy final plus E loss plus work out. Now, in this case, like I did before, The E loss is going to be zero. The workout is going to be zero. I should say that E loss and workout might not actually be zero. Obviously, if you're rolling without slipping, you are losing some energy. Your book takes a little bit of time to talk about how things slow down when they're rolling. And basically, it comes down to the round object becomes less round, and the normal force actually causes a torque on it because the normal force is not aligned with the center of mass. Okay, so we know it's happening. It's just a very small amount. And later, we'll even use a problem like this to calculate what is the actual friction force necessary to have rolling without slipping. Now, we also have rolling without slipping. Oops. We also have rolling without slipping, and that means V equals R omega. So once I put all this in, I'm not going to do like I did last time. I'm going to say y is equal to 0 at r above the ground. Okay, so that the lowest point for each of these objects to go will be a height y, where the center of mass is at a height r, and therefore I'm going to call the potential energy 0 at a height r. So instead of having the h plus r, okay. So what I have on the left-hand side, since they all start from rest, I also have that the kinetic energy initial is zero. And since I'm getting rid of that mgr0, I'm going to have the final potential energy be zero. And I'm going to set this up in a generic way so that it counts for each of the objects. Because what I know is the moment of inertia for the thin hoop, which I'll call TH, is just r squared. The moment of inertia for the solid sphere, which I'll call SS, is 1/2 or excuse me, solid sphere. It's 2/5 mr squared. And the motion or the moment of inertia that I'll have for the solid cylinder is 1/2 mr squared. And for the empty soup can, that's just basically going to be, since it's an empty soup can, it's more or less like a hoop, but it's also got a disc on each end. So maybe I'll say I empty soup can would be equal to, we would probably need to approximate what fraction of the can's mass is in the lids and what fraction of it's in the discs. Uh, and that's directly proportional to the area. So what I could say is the total area of it would be pi r squared plus pi r squared plus 2 pi r h. So area can total is going to be equal to. Now I think I'm well, what my Navy friends would tell me, I'm nuking this. Okay, and they're not wrong, but I can't allow this problem to be solved without thinking about this. So just from a physics standpoint, what I know the soup can will be is it's going to have a can material, which is essentially really thin metal. So it's basically like a homogeneous lamina, is what I'm thinking of it as, which you know, hopefully from calculus or from the previous videos I've made. A homogeneous lamina just means something that if you take off any square centimeter or any square millimeter or any square thousandth of an inch, it's always going to weigh the exact same as any other thousandth of an inch or any other square centimeter or any other square millimeter. That's the density part of it. And the other thing is that the total of it is just going to be proportional. The total mass of it is just going to be proportional to the area. So I can treat the area like a measure of the relative mass. So the area total would be 2 pi r squared. Technically, the volume would be 2 pi r squared times T, where T is the thickness of the lid. I have one lid that's pi r squared. Ooh, and that should be a capital R, not a lowercase r. So 2 pi r squared. And then around the edge here, The circumference of the circle is 2 pi r, and then I'm going to call the height 8. Ooh, I'll call the height, let's say something other than that because I'm using h already. So I'm going to say that L, and this is obviously r. So in this case, it's 2 pi r times L. So that's the total area. So if you want to know the mass of the, let's see, the mass of the lid, that's going to be pi r squared over 2 pi r squared plus 2 pi r l times big M, because we know the total mass would be the 2 pi r squared over plus 2 pi r l. And then we could say the mass of the other lid would be pi r squared over 2 pi r squared plus 2 pi r l times the total mass. And then the mass of the walls of the sides, I should say. So I'll just call side. And I'm talking about the cylindrical part. That's just going to be 2 pi r l over 2 pi r squared plus 2 pi r l, all that times the big M. And really, I should continue calling these lowercase m's just to be sort of consistent. Okay. So now that's the fraction of each mass. I'm thinking they didn't really want you to do that. In fact, let me look at the way they solved it. What did they do? Ba ba boom ba ba boom ba ba boom ba ba. Okay, so they sort of punted in some sense. I was just looking at the way your author handled it. He did acknowledge the problem. It says the empty can, which is a hoop plus a thin disc, uh, has most of its mass concentrated at R. I would agree with that because the most of the mass would be the 2 pi R plus the little rim of the pi R squared, but I'm not so certain that, what fraction the lid is compared to the other part, but this would be actually the process you go through. But what we're going to say is it should be very, very close to just mr squared because a good fraction of the mass is totally at a radius r. But that's only true if all of the masses at a radius are. So we'll do something like approximately 0.99 mr squared. Okay, so it's smaller than 1 because obviously some of the mass is not at a radius r, but it's not that far from 1. So now what we can do is we can say in general, I is some constant k times mr squared. Notice all those formulas are a number times mr squared. And in fact, you can sometimes take the square root of that k and multiply that by the r, and that's called the radius of gyration. So it gives you a measure of what the true, in some sense, true radius is. You could do that, but I'm going to keep the k because the k will give us the right answer. When we just plug in 2/5 for the sphere, or 1/2 for the cylinder, or 0.99 for the empty soup can, so on and so forth. So now I'm going to take my potential energy and I'm going to say, uh, ignore all the stuff I did with the can. That was me showing you exactly how you'd go about figuring out whether we're right or wrong. If we go further and just make the assumption that most of the mass is really at a distance r, then it's probably not arguable to make it any different than 0.99 or something like that. It might be 0.95. It might even be 0.85. I don't know. But the main thing is it's definitely close to 1, but not quite 1. So what I'm going to do is use our conservation of energy, and our conservation of energy is going to be M times G times H, that's the initial potential energy, is equal to 1/2 M V squared, that's the velocity that it has at the bottom, plus 1/2 K M R squared, that's the I, times omega squared. Now I'm going to put that in again. MGH is equal to 1 half MV squared plus K over 2 mr squared times v squared over r squared. So you can see now that the r's cancel out here as well. You can also see that there's a common factor of m in all the terms. So we now have gh is equal to uh, both of these have a common denominator, so I'm going to say it's equal to k plus 1 over 2 times v squared. So V is equal to the square root of 2GH over K plus 1. Now, that tells me that the one with the largest K value is going to be the slowest. So V slowest implies K equals largest. And remember, that's the slowest at the bottom, but that also stands to reason that it'll be the slowest all the way through as the height changes, because we did it for an arbitrary, we did a height h as the total height, but that h could have represented just the first tenth and we still get the same answer. So it's always going to be the different speed. So what this means is when they ask in what order do they reach the bottom, they reach the bottom in the order of decreasing, or excuse me, increasing. Yeah, it should be decreasing k. They all reach the bottom in order of decreasing k. What I mean by that is first has the lowest k, last has the highest k. So when we look at that, the highest k is when we have the factor of 1. So last and first, putting it in this line, the highest k is the thin hoop. And then the next highest is the empty can. And then the next highest is the 2/5, which would be, nope, the 1/2, which is, remember, 2/5 is 0.4, 1/2 is 0.5. So the next highest is the solid cylinder. And then the next highest would be the solid sphere. And that K was 2/5 equals 0.4. This K was 1/2 equals 0.5. This K was approximately 0.99, and this K was 1. So that should be the order. Anybody have any questions on that one? All right. So let's move on to another example. This one is analyze the rolling sphere from the previous example in terms of forces and torques and determine the velocity of the center of mass of the sphere's center of mass at the base of the incline and the magnitude of the friction force. So we're doing that same example again, only now I want to know what is VCM at the bottom of the incline and what is the friction. Okay, so my diagram again is going to be an inclined plane. The height is h. The angle, that was a really bad looking incline. Let me draw this way. Okay. The angle I'm just going to call theta. I don't necessarily know that it's going to work out. In fact, I do know that it's not going to work out, but I can make use of it a little later. And we could call, for instance, this distance from here to here. If we need to, we can call that L. I don't think we're going to have to, but just in case, I had that here. And what we have is a sphere on top whose mass is m. It's a solid sphere whose radius is r, and it's a solid sphere. Now, in this case, we're actually doing a free body diagram, and we're trying to actually calculate what's going to happen using Newton's laws as opposed to conservation of energy. So if I put the sphere right here, I can start to get a little bit more sense of what's going on. I'm going to tilt my axis like such. I'm going to say that's my y prime axis. I'm going to say this is my x prime axis. I am going to say that we have a sphere right here, and that's supposed to be centered up on the. Okay, I'm trying to move this instead of changing the size of it. There you go. Okay. Now, what we have acting on it is here's the inclined plane right down here. Okay. So, what I have acting on it is a force upward that is the normal force. Actually, it's in that automatic draw thing, so let me fix that. That's the normal force. What I also have is the weight, which is equal to m times g. And remember, this angle is theta. So this angle would be 90 minus theta, which would also be this angle is 90 minus theta. So this angle right here is theta. And what that means is I am going to get a component of the weight that is perpendicular to the incline. And then I'm going to get another component of the weight that is parallel to the incline. And this one's going to be mg. Whoa, Nelly. This one's going to be m, and I should be writing it in red. Mg cosine theta, and this one down here is going to be mg sine theta. But in addition to that, I have a friction force right here that is F. That's clearly causing some kind of torque on all of this. You can picture this blue vector, the mg sine theta, you can picture it just like its tail is right here and it's acting that way because I'm drawing it as the mass is acting on the center of mass, which is what we learned about bodies is when the objects actually have a physical size, the forces that we deal with are acting as if they act at the center of mass. So weight, mg, is actually pulling at the center of mass, and if that causes something to rotate, so be it. Okay, so I now have all of that. Now all I've got to do is work out exactly what the equations of motion are. So I'm going to say the summation of the forces in the y prime direction is equal to mass times acceleration in the y prime direction. But we're not expecting this ball to be bouncing up and down on the incline. In fact, we expect the y prime coordinate to stay the same coordinate throughout the whole motion until it gets to that different surface at the bottom. So with that in mind, that should tell us the acceleration is actually equal to 0 in that direction. And all we get for that equation is Fn minus mg cosine theta is equal to 0 because that's all the forces. So we just get Fn is equal to mg cosine theta. I'm just going to put 1 on that, but I don't think we're going to make use of it. Okay, we could, if we really wanted to break it down into mu, into the friction equals mu times the normal force, but I'm not necessarily trying to do that either. So I now want to take the summation of the forces in the x direction, x prime direction, is equal to mass times acceleration in the x prime direction. And the acceleration down the incline is definitely a real thing. If it wasn't for friction, we'd expect it to be g sine theta. So in this case, I'm not going to say A is 0, but the forces that I see acting on it are basically just mg sine theta minus the friction force. So this is going to become mg sine theta minus the friction force, which I write with a script F. Your book does a regular F, and then it does like a script FR for friction as a subscript. I just call it F like this. And this is going to be equal to M times A. I'm going to call that equation 2. Now, in addition to all this, we also have a summation of the torques is equal to I times alpha. So the summation of the torques is equal to I times alpha is another equation. And in this case, I'm not worried too much about the signs, but what I'm going to do is I see that the friction pointing in the negative direction like it does is tending to cause the wheel to rotate in a clockwise direction, which is exactly the direction it should for it to roll down the incline. So I should probably try to link them so that the friction is positive, or excuse me, the friction is negative when the acceleration is positive, and that would actually cause a torque that is consistent with a rotation being positive. So the way I'm going to write that is I really only have one thing applying the torque. The normal force is acting at the center of mass. The center of mass is the rotation axis. So there's no torque due to the normal force. The mg is acting at the center of mass. The axis of rotation is the center of mass. So again, there's no lever arm for that one either. So all we have a lever arm for is the friction force F. And notice that's exactly perpendicular to the radial line R. So the torque in this case is just going to be F times R. And that's going to be equal to, in this case, we're doing, didn't I think we said with a solid sphere? Yeah, it's a solid sphere. That's going to equal I, which is 2/5 mr squared times alpha. Okay, so that's going to be equation 3. So now we have all that, and that's kind of nice, but we can actually use this because we know it's rolling without slipping. So rolling without slipping, oops, that gives us V is equal to R times omega. And that also gives us A is equal to R times alpha. So if you took, let's say, oh, let's take equation 3 and divide it by R. When I do that, I'm going to get what I call 3 prime, and this is just F is equal to 2/5 M times, notice there's only one R left, so it's R times alpha, and R times alpha is actually A. So now I'm going to plug 3 prime into equation 2. When I do that, I get mg sine theta minus 2/5 m times a is equal to m times a. Now, what I've done is I've eliminated all the unknowns except for A and theta, but I probably can figure out something to get rid of theta. So what I'm going to do is get the A's on one side, and that's going to become 2/5 positive on the other side. 2/5 plus 5/5 is 7/5. So I'm going to get mg sine theta is equal to 7/5 m times a. Now we can see, which we could have saw it earlier as well, I can divide through by the mass, and that tells us our result is going to be independent of the mass. And that's a good thing. Again, things fall at a rate independent of their mass. At this point, we can go ahead and figure out that A is therefore equal to 5/7 g sine theta. But if I look at that triangle, I see that sine theta would be actually h over L, where L is the distance that it travels down the incline. So I can go ahead and say A is equal to 5/7 times G times opposite over hypotenuse, which would be h over L. Therefore, we know A is equal to 5 GH over 7L. That's our actual result, and that actually happens to be the right answer, by the way. And let me double check something. What they wanted was, what did I ask for? What is the V cement at the center of? Okay, so that's the acceleration. I shouldn't have boxed that off because that wasn't one of the solutions we're asking for. But now I can use V squared is equal to V0 squared plus 2A x minus x0. That's one of our kinematic equations. We're taking it where it started from rest, so V0 is equal to 0, and x minus x0, that's just going to be the distance traveled, so that's going to be L. So I can say v squared is equal to 0 plus 2 times a, which is 5gh over 7L times L. So that gives us that the velocity of the center of mass is actually going to be equal to the square root of 5gh over 7. Now that is one of the things they asked for. Now, in addition to that, we can now use equation 3 prime to figure out what the friction force is. And equation 3 prime says the friction force
What happened
is,
to the two when you multiplied the acceleration by two?
I just made that up. I use a virtual version of mathematics that not everybody's aware of, that where 5 is the same as 2, it's 10. In other words, yeah, I screwed up, dude. Good job. Nice catch. I'm glad you were paying attention. That's awesome. And actually, it's weird because I was sitting there thinking I could have sworn I got a 10/7 there, not a 5/7, but I didn't pay enough attention. So yeah, absolutely right. That 5 times 2 should have became 10. So it's the square root of 10 GH over 7. Which notice, by the way, was the exact same value we got before when we did the square root of 10 GH over 7. So isn't that amazing that we got the same result? Well, once you corrected me on dropping my 2, we got the right answer. Thanks for that, by the way. Was that Aiden? Or who said that? Oh, secret. No problem. Anyway, so here's the F. The F is supposed to be 2/5 times M times A. We know what A is. A is 5GH over 7L. So I'm going to say 2/5 M times 5GH over 7L. You can see that the 5 cancels out with the 5, but that's pretty much it. So what the actual friction force is F is equal to 2/7 M, oops, it should be a capital M, M G H over L. So that should be the friction force. Anybody have any questions on that one? Now, you could replace that H over L with sine theta if you want, and that's actually a pretty valuable way. So it relates it to the actual angle of the incline. Let me do that just to sure it up. So now what we're saying is this is also equal to 2/7 mg sine theta. Sorry about that looking so narrow, but I was trying to fit it in, obviously. So there's your sine theta, mg sine theta. Any questions on that one? All right, so those are the two major types of problems I wanted you guys to be able to do. I wanted you to be able to use conservation of energy to solve rolling without slipping down an incline, calculate the final velocity at the bottom of that incline, but I also want you to be able to do it with Newton's second law. I've now shown you a couple of examples like that. You can see this one, which was conservation of energy, this one, which was conservation of energy, and the example one, of course, that was just calculating the kinetic energy. But this one is using Newton's second law to actually analyze the motion. And oddly enough, we were able to get exactly the same results. So, anybody have any questions on that? All right. So now that we've done that, I need to hit a couple of typical examples from chapter 11. What I want you to understand about chapter 11 is this chapter is called Angular Momentum and General Rotation. So I'm going to say chapter 11, Angular Momentum and General Rotation. So that's our motion. Now, the biggest thing I need you to understand on this is we need to have some idea of what angular momentum is. Well, for instance, we know that P in linear motion is equal to mv, and we know, or at least I've hinted at you, that the rotational analog to linear momentum is angular momentum, and the symbol we use for that is a capital L. So if you look at the rotational analog to mass, can anybody remember what variable we use in rotation that's sort of equivalent to mass? I'll give you a hint. The unit includes kilograms, but it also has something squared that's not kilograms. The rotational analog to mass is moment of inertia, so it's I. And the rotational analog to velocity is angular velocity, which is omega. And if you paid attention to chapter 10, you know that we have a whole vectors idea associated with angular velocity, so that basically when you're looking at something, let's imagine like this circular disc rotating, right? Every little vector in that disk is an equally justified candidate to represent the angular velocity of it. There's no good reason to choose this direction over this direction over this direction or this direction. In fact, all of them are equally crappy, right? But when you see the object is actually rotating, you can reduce the number of choices to two by choosing a direction perpendicular. So we can say it goes that way or it goes this way. So when it's rotating, on the in the plane of the paper or in the plane of the screen, then we can choose the vector representing that rotation as pointing into the page or out of the page. What we do is we eliminate one choice by assuming that me, the right-handed person, and all the other right-handed persons in the world are superior to the left-handed people in the world. No, we don't really do that, but there is a long history of us sort of treating that like it's not a good thing. But we do use the right hand. So if you see something rotating like this, if you curl your fingers in the direction of rotation, notice my fingers are curling in the direction of rotation. I'm doing it with my right hand. My right thumb points the direction it's going. That's our vector direction associated with angular velocity. Torque has a similar one, and your book even talked about pseudovectors. That's what happens whenever you take a cross product. So this angular velocity is a pseudovector. But I'm also going to tell you that there's another form. If you want to know the angular velocity of a particle, or excuse me, the angular momentum of a particle, I'll say L particle is actually equal to R cross P, which is equal to R cross MV. Again, as long as we're staying in classical physics, the M times V is the momentum, but in relativity, we have a different formula. So, as long as we're not dealing with relativistic stuff, we're good to go on that. Now, the other part is we had Newton's second law, which said the net force acting on the system is equal to dp dt. Remember, I told you that's specifically what Newton gave us in his Principia rather than m times a. M times a is a special case. The dp/dt is the general case. Well, the rotational analog to this is the summation of not the forces but the torques is equal to not dp/dt but dl dt. Therefore, if the net external torque acting on the system is zero, then dl dt equals zero. And what does it mean when the derivative of something is equal to zero? I suspect y'all
It's
know,
not
and you're
changing.
exactly, it's a constant. So L is equal to a constant. And I'll put a vector symbol over it just to remind you that it's a vector constant. That is the statement of conservation of angular momentum. So this is the reason your book has an ice skater in the opening page of chapter 11. This is the reason that an ice skater, when she has her hands up like this over her head or even down by her side, the arm weight is actually closer to her rotation axis than it is when it's by her side, and especially when as it is when her arms are sticking straight out. So the moment of inertia of the girl is actually a lot larger when her arms are spread out like this, and a lot smaller when they're up like that. So because of that, we're looking at uh, L1 equals L2 as conservation of momentum. That means when our arms are down, we have a little itty bitty angular, or excuse me, moment of inertia, and we have a big angular speed. Let's say arms up, and I mean completely up overhead. But if the net torque acting on the ice skater is zero, and imagine this, she's actually on the little tips of her blades. Those little tips of the blades are not very far off the line of rotation the axis of rotation for her body. So the torque that that could do is very, very small to begin with. But the fact that it has almost no lever arm means it's even smaller still. So the torque is essentially zero. And when she goes to having her arms extended perpendicular to her body, then the moment of inertia becomes really large, but the angular velocity becomes really small. So, for instance, you could have something like 5 times 100 is equal to 100 times 5. That's what I mean by small I, big omega, and then that equals big I, small omega. But any numbers, I happen to choose 5 and 100 for the right. I could have chosen, uh, let's say, I could have chosen 250 and then 2. That would work as well. So that's what conservation of angular momentum is. It's I times omega equals I times omega. Or if it's a particle, it's R cross mv equals R cross mv. So let's look at some examples in hopes that this will help you better understand what we're doing here. So we have our equations. I omega is a way of measuring the magnitude of the angular momentum. If it's a particle, the angular momentum is the momentum of the particle, which would normally be the vector mv. But now we're going to take r as a lever arm vector. It points from basically the center of rotation of the system to the actual particle itself. That's the r vector. And therefore, you end up getting, when you say L equals r cross mv, you can get the magnitude of r times the magnitude of m times the magnitude of v times a sine of the angle between r and mv. And that basically tells you, oh, it's the component of r perpendicular to p. So another way of interpreting this is the magnitude is equal to r perpendicular times p, but it's also equal to the component of momentum perpendicular to the lever arm. R, it's r times p times the sine of theta. So all that stuff is fair game. Let's look at a particular example. So what we have here is a table. It's got a itty bitty hole in it, and we've got a string that comes out and in fact is a distance r. And let's say this distance r is equal to 12.0 centimeters. And let's say its velocity at that particular point, v sub big R, is equal to 2.5 meters per second. And down here at the bottom, you can see that there's someone holding this rope. If they go and take and pull the rope down, then the table will start looking noticeably different, specifically because now the radius is quite a bit smaller. Let's say R, which is the distance from here to here, let's say R is equal to 3.00 centimeters, and this mass, M, stays the same, M, but now I've got a velocity at lowercase r. And what we want to know is what is the velocity at lowercase r? Okay, so notice by pulling down on the string, there's no way you can put any torque on the system, right? Torque on the system has to be a force applied at some distance away from the rotation axis. The rotation axis is the hole in the tabletop, so there's no way this, pulling down of the string put any force perpendicular to the string. It just put a force parallel to the string. So therefore, the summation of the torques is equal to zero, and that means linear moment, or excuse me, angular momentum is conserved. So in this case, we have L at big R is equal to L at little r. Well, L at big R is, notice the velocity times the m is perpendicular to the radial vector r. So it just becomes m times v times r. So I'm going to have big M times v times big R is equal to, now the other velocity, and by the way, that's v with a subscript r. And then the other one is m times v with a little r times the little r. So I can now calculate that v, the little with the little r subscript, is equal to, notice the masses drop out, that's why I didn't give it to you. What I get is v sub little r is equal to big R divided by little r times v sub big R. So the big R was 12.0 centimeters, the little r was 3.00 centimeters, and the velocity v sub big R was 2.5 meters per second. And 12 divided by 3 is 4. 4 times 2.5 is 10. So I get 10.0 meters per second is V sub little r. Any questions on that one? So that's a typical conservation of angular momentum problem. Another typical conservation of angular momentum problem is a clutch. And your book took the time to draw basically a clutch, which you can imagine it as sort of two ovals, which actually they're two circles. It's just when we see them rendered in two dimensions, they tend to look like ovals because we're not representing the whole thing. But what you might have, for instance, is this bottom device, which would be connected to, say, the camshaft or whatever coming out of the engine. So this would actually rotate with some angular speed omega 1, and then this guy, which has a mass m and a radius r and is not speeding, so omega is equal to 0. If you just drop this on top, the net torque on the system, since you're counting the system as this object, which is MA, plus this object, which is MB, if you drop MB on MA, then they are applying torques to each other, but they're part of the system, so those are internal forces. So when you drop it, then the summation of the torques is equal to 0, which means momentum is conserved. So L is conserved. So that means I omega for A is equal to now I A plus I B times omega nu, and I'm just going to call that omega 0 for, or excuse me, omega 1 is what I should have called that because I already labeled it omega 1. So if I treat this as a disk, then I know the moment of inertia is 1/2 mr squared and then times omega 1. And now after they stick together, I have 1/2 ma, and this was ma by the way as well, ma r squared plus 1/2 mb r squared. The r's are exactly the same, and I get omega. The omega is what I want to know. I want to know the final velocity after these two clutches come into contact and they reach some kind of equilibrium. What I'll find is omega, the new velocity, is equal to 1/2 ma r squared over 1/2 ma r squared plus 1/2 mb r squared. All that times omega 1 And that's how conservation of momentum is done in that case. Any questions there? All right. Well, we've actually reached the time. I have a couple more examples I'm going to do from chapter 11. I have a couple more I'm going to do for 14 and 15. Now, what I need you guys to do is I need you to pay close attention to my YouTube channel for when I post things. I'm just posting them directly to YouTube. So please subscribe to my channel just until the end of the semester at least, and then just throw it away. It's fine. Feel free to recommend it to other people, by the way. I'm not making any money off this. Maybe one day I will. God, I hope I would. That would be awesome. But I can't imagine I will. So don't worry. I'm not trying to rip you off or anything. I'm just saying subscribe to it so you'll get an email every time I post something new, and you'll be able to look by the title of what I post to tell whether it's 241 or 242. And when I look Friday or Saturday afternoon, or excuse me, Sunday afternoon, when I look, if I see that, all of you have been actually watching the videos, and then I look in the mastering and I see that chapters 14 and 15 homework are done by virtually everybody, then there's a good chance I might not put 14 and 15 on the final exam at all. Okay. So try to do that. The other thing is, you guys have me for lab where we normally meet on Tuesdays. I've been sort of sandbagging on grading the labs because I have a lot of students that haven't turned them in. I am going to update all the grades tomorrow. So whatever labs you don't have turned in by tomorrow, there's a good chance you're going to have points taken off for them being late. All the ones that are in by tomorrow when I start studying, when I start putting in grades, I'm going to count them as if they're fully there on time. And if you got 100, you're going to get 100. So that's just your last warning. I just want to make sure, try to get your labs in case you've been, just waiting, putting it off, not putting it in. Just put them in before I get to grading them tomorrow. I would start, like I said, with like at lab number 3 or lab number 4, one of the early ones, and put that in, then lab number 4, then lab number 5, then lab number 6, so on and so forth. That way, there's a higher probability because, I grade them in the order that they're actually created. So lab 1, I grade first, which I already did lab 1, 2, and 3. But labs 4, 5, and 6, that's what I'm going to next. So try to get those in. You guys are free to go. I'm going to wait here till the last person leaves, and in case anybody has any questions. But keep an eye on your email and pay attention to me posting videos to YouTube. And have a great, safe weekend, even though it's only Wednesday, so don't start till Friday. But thanks. Make sure you chat me your first and last name if you hadn't already.